Welcome to the Explainer, everyone. I'm seriously thrilled you're joining me today because we are going to dive into one of the absolute most fundamental ways we understand the universe. And to do it, we're going to imagine this grand, gigantic scientific city. Let's call it Spectroscopia. In this magnificent place, every single building, every machine, every lab, it all exists for one exact purpose: to figure out matter by watching how it interacts with light and energy. If you've ever wondered how scientists look at a distant star and know exactly what it's made of, or how they spot a totally microscopic flaw in a material, well, you're in exactly the right place. Okay, so let's pull up our master map. This is basically our ultimate guide to the city. We're about to take this continuous, sweeping tour through the 11 distinct districts of spectroscopy. And as you'll see, every technique mapped out here, from the bright, colorful, visible spectrum up top, all the way down to those super intricate charts of magnetic resonance, it's really just a different type of conversation between energy and matter. It's such an incredible journey, and I'm going to walk you through exactly how all these pieces fit together to build a complete scientific civilization. So here's our itinerary for the tour today. First up, welcome to Spectroscopia. Second, what matter takes and gives. Third, delayed light and whispers. Fourth, surfaces, structures, and magnets. Fifth, thin films and mystery waves. And finally, number 6, the universal machine. All right, let's jump right in.
Section 1. Welcome to Spectroscopia. Let's hit our very first stop and see how this whole thing gets built. We're starting right at the entrance to the city, inside the source chamber. This is literally where our traveler, energy, is born. Because think about it, before we can interrogate matter, we need a voice to ask the questions, right? And in this city, that voice comes from a tungsten lamp, a laser, an X-ray tube, or maybe even a radioactive source. Now, the key takeaway here is that this voice is actually the oldest guide in physics, light. But we're not just talking about the stuff we can see. Spectroscopy uses the entire electromagnetic family. We're talking massive radio waves and microwaves, straight through infrared, visible, and UV light, all the way down to those really piercing X-rays and energetic electrons. But raw light? It's chaotic. So the city runs it through prisms, gratings, and filters just to organize that energy into very specific wavelengths, because the cleaner and more precise that voice is, the deeper the answers we get from matter. Section 2. What matter takes and gives. Moving along, we're entering our first true districts, the Valley of Absorption, and right after that, the District of Excitation. This is where we get down to the basics of what matter takes from our light and what it hands back. So over in the Valley of Absorption, scientists basically just shine light straight through a sample. But here's the magic question. What happens when that incoming light exactly matches an energy gap? Since electrons and molecules are totally bound by quantum rules, they can only jump between very specific allowed energy states. When the light is a flawless match, boom, the molecule just absorbs it. The detector on the other side sees a dip in the light coming through, and that missing energy, that specific little dip, that becomes the absolute unique fingerprint of that exact material. A classic example of this is UV-vis spectroscopy. You pass visible and ultraviolet light through a colored solution, and as you tweak the wavelengths, electrons start jumping around. This perfectly shows off the mathematical heart of the whole process, the Beer-Lambert law. Basically, it says absorbance depends entirely on the concentration of the solution and how far the light has to travel through it, the optical path length. Just by tracking which wavelengths vanish, we can precisely measure chemical concentrations, or even characterize things like nanoparticle and semiconductors. But wait, what if we totally flip the script? What happens if we energize the matter first? That question pulls us right over into the District of Excitation. So instead of looking for the light that goes missing, we're going to look at what matter actively throws back at us. When you pump energy into matter right from the start, like inside a super hot flame or a plasma chamber, those atoms get wildly excited and totally unstable. But it doesn't last long. They relax pretty quickly. And as they do, they emit light. Every single type of atom glows in its own unique way, giving us a fingerprint made entirely of photons. Sodium gives off this brilliant yellow, copper shines a really vibrant green. Our spectrometer separates out those emitted wavelengths, and suddenly, boom, chemistry becomes astronomy. I mean, the exact same principles we use in a tiny lab plasma chamber are how we figure out the elemental makeup of stars millions of light years away. Crazy, right? Section 3. Delayed light and whispers. All right, let's keep wandering into these really beautiful glowing neighborhoods of fluorescence and Raman scattering. The conversations between energy and matter get a little more sophisticated here. We're talking about delayed light and really subtle whispers. Welcome to the realm of fluorescence.
Here, matter absorbs energetic light, sure, but before it spits it back out, it loses a little bit of that energy internally. Because of that energy loss, the light it re-emits is lower energy, which means it has a longer wavelength. This delayed light makes materials literally glow in the dark, revealing all sorts of hidden electronic behaviors. It is absolutely crucial for things like bioanalysis, zeroing in on targets in cancer imaging, and studying advanced quantum dots. Right next door, we're tuning into what I love to call the whisper of molecular structure. When you blast a laser at a sample, the vast majority of those photons just bounce right off, totally unchanged. That's really scattering. But a teeny tiny fraction of those photons actually trade energy with the natural molecular vibrations of the material. That causes this microscopic shift in frequency, known as the Raman shift. By tracking these unbelievably subtle energy whispers, scientists can map crystal structures, detect hidden stress in a material, and analyze complex stuff like graphene or pharmaceuticals. Now, what's genuinely fascinating is how Raman compares to another heavy hitter in the city, FTIR, or Fourier Transform Infrared Spectroscopy. They both investigate molecules, but they essentially speak different dialects. Deep in the infrared hall, FTIR uses an interferometer and some intense math to listen directly to how molecular bonds stretch, bend, and twist. Raman, on the other hand, watches for changes in a molecule's polarizability. So they're really like complementary twins. Used together, they give us this complete, high-definition picture of the molecular dance. Section 4. Surfaces, Structures, and Magnets. Okay, gear up for a major perspective shift. Things are about to get a whole lot more microscopic. We're leaving bulk materials behind and zooming way in to look at atomic layers, deep internal architecture, and magnetic behaviors. Welcome to the surface kingdom. Down here, we literally only care about the very outermost layers of atoms. In XPS spectroscopy, or XPS, we bombard a material with X-rays until its core electrons just fly right out. We measure how fast they're moving, their kinetic energy, and leaning on the law of energy conservation, we calculate their binding energy. That single calculation unlocks the exact elemental makeup, oxidation states, and chemical bonding right on the surface. XPS, along with its deeper diving cousin Auger electron spectroscopy, is pretty much the ultimate language of surface chemistry. Digging just a bit deeper into the atomic neighborhood, we hit X-ray absorption spectroscopy, or XAS. This one is super cool because it splits into two main regions: ANAS, which maps out the electronic structure, and EFAS, which actually reveals the physical atomic arrangement. With XAS, matter stops just telling us what it is and actually starts showing us how it's built, stuff like precise bond lengths and coordination numbers. Combine that with electron microscope techniques, and scientists are literally analyzing matter atom by atom. And then the whole city just kind of quiets down. We're entering the district of nuclear magnetic resonance, NMR, and Nussbauer spectroscopy. You won't find any optics or lasers here, just massively powerful magnetic fields. See, atomic nuclei actually act like tiny spinning magnets. Drop them into a strong magnetic field, hit them with some radio frequency pulses, and they'll emit specific signals as they settle back down. This is how we map incredibly complex stuff like protein folding. And hey, if you've ever had an MRI, you've directly experienced a giant medical version of this exact NMR physics. Right next door, Nussbauer spectroscopy uses recoil-free gamma rays to probe iron chemistry and oxidation states, which is an absolute game-changer for geophysics. Section 5. Thin films and mystery waves. We are nearing the very edge of spectroscopia now. This is the frontier, the domain of super-thin films, polarized reflections, and these mystery waves that sit right in the gaps of our familiar spectrums. There are some wild applications out here on the edge. First up, sandwiched right between microwaves and infrared, is terahertz spectroscopy. THZ radiation probes carrier transport and dielectric properties. It's literally the bridge between electronics and photonics, making it essential for things like semiconductor testing and advanced security scanners. Then we've got ellipsometry. For this, scientists bounce polarized light off thin films and measure the change in amplitude and the phase shift when it reflects. From just those changes in polarization, they can calculate film thickness and refractive indexes down to the nanometer. There is absolutely no way we could build modern solar cells or microchips without it. Section 6. The Universal Machine. All right, we've walked the streets of the whole city. Now it's time to pull back the curtain. Every district we visited seemed totally different, right? But there is this one hidden infrastructure that literally connects every single building in Spectroscopia. When you look closely, you realize a spectrometer is never just a single machine. It is a complete system, and almost every single one follows this exact same universal flow. Step 1. An energy source creates your photons, electrons, or X-rays. Step 2. A wavelength selection system dials in the exact spectral content you want. Step 3. That light enters the sample interaction region. This is the arena where matter actually responds. And step 4, the detector catches that response, instantly converting the energy into electrical signals.
But the journey obviously doesn't stop at the detector. Step 5 brings in the signal conditioning electronics to filter and pump up those signals. Step 6 is the data acquisition system, which digitizes everything. Step 7 leans on computational analysis to turn that raw, messy data into those gorgeous, readable spectra we rely on. And finally, Step 8, interpretation. This is the real magic right here. It's the moment physics turns into chemistry, chemistry turns into structure, and structure becomes deep, tangible human understanding.
At the very end of our tour through Spectroscopia, there's just a single inscription, and I think it perfectly sums up everything we've looked at today. It reads, "Matter cannot hide from energy." Because whether we're asking what atoms are in there, how they're bonded, how they're vibrating, or what microscopic flaws they have, matter always, always answers. And it answers us through spectra. And honestly, that is the true story of spectroscopy. It's the art of seeing the invisible, just by using the language of energy. So as we wrap up this explainer, I want to leave you with one final thought to chew on. Now that you know the rules of this incredible city, how might you use the language of energy to decode the invisible world around you? Thank you so much for joining me on this deep dive into spectroscopy. Keep observing, keep asking questions, and keep learning. Catch you next time.